Seems like there is. Yeah. Your eyes pop out in a minute.
Okay. So among other things, we're going to talk about gases. You guys dealt with gases in last week's lab. And actually the air does change from place to place, time to time. We'll talk about impurities. And we'll kind of end the chapter, ultimately kind of talk about how we can limit those things that are detrimental to health that are in our atmosphere. I apologize in advance. I didn't do a spell check before I hope I caught all my typos. I don't know. So here's a your turn thing. So maybe I fixed it. Does it say ground print on yours? I think so. Okay. So we are leaving our ecological footprint. Each person, each generation, each society, okay? You've probably heard, or maybe you're familiar with the concept of looking at your carbon footprint, for instance, your ecological footprint. So one of the things I just want you guys to do, take a minute and, Natalie, take a minute. Now it's your turn. It's your turn, Natalie. So go ahead and identify 3 things indoors and 3 things outdoors. So just take a minute on your own, and we'll kind of see what you guys have. We'll do shout outs. So 3 things indoors and 3 things outdoors that are in the air that you breathe, or that emit things other than nitrogen and oxygen in the air that you breathe. So indoors and outdoors. Now I like to tell people that if you can smell it, it's a gas and you are interacting with it. So I'll just kind of get the ball started, and you can use this if you want to. Indoors and outdoors, we have perfumes or deodorizers, okay? What other things indoors and outdoors emit chemicals? Think of I want to tell you, I don't want to do it for you, but just think of like cars or factories. So jot down. Remember, you're getting participation points for this. Jot them down, and I'll ask what you got.
One for mark that are indoor and outdoor, and 3 for indoor, 3 for outdoor.
3 for indoor, 3 for outdoor.
Okay.
So they put carpet in the room next to us, and I think it helps absorb some of that sound of their Zoom.
Put carpet over there.
Yeah, we don't know. But I think it helps with that sound, because remember?
I felt like the stove top in the oven. Sometimes people accidentally leave it on, or it comes off that gas stove. Isn't that good enough? Improvement? Oh, anything's improved? Oh, wait. Is debug? I think it's even better. I don't know. Essential oils? Essential oils are good though. They are good. Yeah. We're talking about endurance. Yeah, what improves endurance? You guys are better than me. I'm over here just spacing out.
Okay. So we'll see what y'all came up with. We'll pick on Natalie first in case everybody says her answers. So, Natalie, what's one of the ones indoors you have?
Candles.
Candles? Oh, I like it. So you'll say one, and then can you tell me of these three, do you think in general they hurt the air quality, improve the air quality, or some have some effect, but you're not quite sure?
Hurt the air quality.
Hurt the air quality? I could see that, maybe the particulates or people reacting to it. Very good. So Billy, what did you have for an indoor?
Cleaning stuff.
Cleaning stuff?
Chemicals.
Yeah, very good. So what do you think is with regard to air quality? Have anything heard it? We're all gonna die. Okay. Glenna, what did you have for indoor?
Like hair products.
Hair products.
Like hairspray. Stuff like that.
Very good. What do you think with regard to air quality?
It's probably hurting.
Probably pretty what?
It's probably hurting.
Probably hurting the air quality. Okay. I mean, I'm just guessing too. I can definitely see a case for being made. Let's switch to the outdoor ones. So, Autumn, what do you have for an outdoor thing?
That hurts or
Just say what it is and then say what of these three categories it falls into.
cars hurt.
Cars hurt the air quality. Yep.
Gas-powered cars for air quality.
What's that?
Gas-powered cars for air quality.
Gas power?
Yeah, but so do electric because we're made of the emissions.
Not so much.
But just getting to an electric.
Yeah, they're not neutral. Neither cars are not environmentally neutral. Okay, Taylor.
I put a bonfire.
Bonfire?
Probably hurt the air quality.
Or generally hurt the air quality. We didn't have anything improved.
Algae improves.
Algae is a way, yeah, plants are a way of actually at least taking, not the particulate as much, but at least taking the carbon dioxide in and maybe even other things. So I have this short little video. It's short, I promise. It's not a 15-minute or anything. Yeah. It gets a little tricky because it kind of, that's a good point, look at that, yeah, 1,727 degrees Celsius. But the air is so thin that it really doesn't retain its heat, so the little particles are so far apart. In order for something to be hot, you have to have a particle there to be hot. So it's kind of farther between the gas particles. And the other thing, I think this is right, if this was right to say it this way, is it kind of depends on if you're turned towards the sun or away from the sun at those higher elevations. To me, that would be a daytime temperature.
What is like the spaceships? And well, I guess it's taking up space, so it's especially right.
The spaceship, yeah, the spaceships up there though don't have much resistance because the air's so thin up there. It's interesting. Interesting. Air is awesome. So one of the things in lab we talked about is most of the air we're breathing in is nitrogen. So it's about 80-20 nitrogen, oxygen. Would you say it's a homogeneous or heterogeneous mixture? What's that?
Hetero, right?
I would kind of say, I'd say it's pretty well mixed. I'd say it's homogeneous. In general. It doesn't form layers. Not in the troposphere anyway. So actually I'm just talking about the troposphere. So the troposphere down here. So the stuff we're breathing is about 80-20 nitrogen and oxygen. So we inhale the 80-20, which the slide says 78-21. Close. So what goes up when we exhale? Like which of these gases goes up as we exhale? Carbon dioxide goes up, exactly. You guys did a test for carbon dioxide in lab, so it goes from 0.04 to what we inhale to 4% what we exhale. And not so surprising, what goes down in what we exhale relative to what we inhale is the oxygen. So I've kind of heard, it's been a while, but medically speaking, our lungs could be more efficient than they are.
How does the nitrogen stay the same?
The nitrogen stays the same because as it comes into our lungs and interacts with our tissue, our tissue doesn't really care about it. It just goes back out.
So it just takes the oxygen from the kernel off the nitrogen.
Yep, it just takes the oxygen gas and lets the nitrogen come in and out. Yep. So we're going to be talking a little bit about concentrations, dabbling in how concentrated something is. And I think we talked about percents before, but just to remind you what that means. Percent means parts per 100. So these are usually, these aren't volume, I think these are weight percents. Yeah, so for example, this is the grams of the component. So for instance, nitrogen, you're looking at 78 grams of nitrogen in 100 grams of air. That's what that means. 78% nitrogen, 78 grams of nitrogen in 100 grams of air. Oh, it says that these percentages are in volume. These are liters of component for 100 liters of liquid. Sorry, these aren't by mass. These are by volume. Why do you think the water says variable? Because, yeah, it depends on what climate you're in. Like if you're in South America, or if you're in the Arctic, you're going to have different amount of water. Now remember, this is water vapor. This is water gas. This isn't water liquid, water gas. You think there's water in this room? Like liquid? Sorry, gas, water, yeah, there's water, gas. Yep. Cool. So in general, depending upon where you are and kind of it varies from day to day, but you're running the atmosphere with regard to water runs about 0 to 4%. Depending, and we use the word humidity. You've probably heard of humidity. High humidity means there's a lot of water vapor. Low humidity means the air is pretty dry with regard to water vapor. So what do you think that blank in is? As a gas, it's blank, but when it converts to a liquid, such as streams or clouds, it can be seen. I think it's invisible too. So when I talk about weather, and I love clouds. Let's just say I love clouds. So clouds are basically water that is now in its liquid state. So anytime you see a white, fluffy cloud, that's water. It's not gaseous water, but now it's water in its liquid state. We call this process of going from a gas to a liquid starts with the letter C. What do you think? Condensation. Yep. Condensation. Yep, you got it. So you can see this, but this is invisible. Now, I don't think we've talked about physical phases of matter. All the physical phases of matter are, we have gas, liquid, maybe we have. What's the other physical phase of matter? Solid. Solid, yep, you got it. So listed here are the 4 physical phases of water, cute little water particles. Okay, we have an iceberg, okay. So of course the iceberg is solid, it's floating on liquid water, and then it's kind of showing you in the atmosphere would be these water vapor particles. So that's all it's showing. I don't know if you can tell, but of these two, this is a good little figure. Of these two that are kind of showing you liquid water here in the left and solid water here on the right, which one looks more crammed together? The liquid water. The liquid water is more crammed together. The liquid water is more dense. Okay? So one of the things, if you mix two things and something's more dense, the thing that's more dense will sink and the thing that's less dense will float. So that's exactly why we see ice. When you guys get ice water, your ice will float under the liquid water. So that's kind of, and actually water is unique like that. A lot of things, as they solidify, will become more dense. So oxygen. I went ahead and put this because I thought this was important. So right now we're about 20% oxygen. We used to be 0% oxygen, okay? When the planet Earth first formed, its first gas was probably mostly hydrogen gas, but then it formed a crust. It was liquid at first, and then it formed a crust, and then it began fissures in the crust, and then kind of, I call it burping. So we had a lot of carbon dioxide come into the Earth's atmosphere. So its first atmosphere was mostly carbon dioxide. Okay, and what likes carbon dioxide? Plants do. I'll answer my own question. So this kind of goes back what Autumn said, is we can actually use plants as our friends if we have extra carbon dioxide or if we just want to purify our air. You know, definitely they can be helpful. Now, a basic plant is algae, but now algae is water loving. Algae is a water plant. So actually early on, this algae were in these big oceans. And they did their thing. They did what green plants do. They took in some of that extra carbon dioxide and they spit back oxygen. Okay? So over millions of years, eventually we got oxygen to form, or oxygen to go ahead and begin forming from this algae. But one of the things about oxygen is very reactive. So right away, it actually started reacting with the metals in the Earth's crust. And if we look back at the Earth's crust, at the minerals in the Earth's crust, a lot of times we've been kind of seeing like the silicates, oxygen and silicon, the aluminates or lumicates or whatever, aluminum and oxygen. So a lot of our minerals have that early oxygen in them, okay? So it took the plants, it's almost like the plants, I can imagine, they were building up. They were spitting out, taking in carbon dioxide, spitting out oxygen. The first oxygen was consumed to make the minerals we all know and love. Well, eventually it built up to create the 20% that we now have. And of course, animals need oxygen. One of the things about oxygen, I'll go ahead and erase this, is oxygen is needed to burn things. Burning or combustion is incorporating oxygen in things. So in general, if I have something that contains carbon and hydrogen, I'll just put kind of an XY here because I don't know how many carbons, I don't know how many oxygens. And I'm going to combine it with oxygen. It's going to form, what's that? Water. And what's this? Carbon dioxide. So in general, this is what combustion looks like. I kind of didn't know where to put this, so I'm going to go ahead and put this right here, if that's okay with you. Do I put it later? I don't know. But this O, this is oxygen. I'm going to go ahead and put a little 2 here. I feel like I might have already said this. There are, if we grab our periodic tables, this is sounding kind of familiar to me, to you guys. If you grab your periodic tables, which I didn't grab mine, go ahead and grab your periodic tables. What is, nice cat. Well, I'll just answer it this way. Find hydrogen, oxygen, fluorine, bromine, nitrogen, iodine, and chlorine. Are they kind of near each other? Like a J. Yeah, they kind of make an L. And then the 7. They make a 7. I like that. Almost named our last child 7. So the thing about these is they are diatomic. What's the word di sound like? 2. Yep. And it kind of has to do with how their electrons are and everything. But they always like to be in 2s. So do you see how I put a 2 here? I'm going to do that with everything up here. So I'm going to put a little subscript 2 here for hydrogen. So hydrogen never likes to be alone. It likes to actually have 2 hydrogen atoms. And I'm going to put a little 2 here for oxygen. Now this is not a compound, okay? And then I'm going to put a little 2 here next to F for fluorine. Put a little 2 here next to Br for bromine. A 2 for, what does N stand for? Nitrogen. I'm going to 2 there. What does I stand for? Iodine, yep, iodine. The 2 there, and what's a Cl? Chlorine, yep. So those little subscripts, and that's, I'm glad I got that on my test. So that's why when I show oxygen, it won't just be an O, it'll be an O2. Now, years ago, I learned this by, I think it's, I don't even know if it's really a German surname, but the name Hofbernickel, sort of like that. If you think of the word Hofbernickel, actually, we have it here in these 7 diatomic elements. Hofbernickel, Hofbrnickel. It's funny the things you remember, right? Hofbernickel. That's isn't that normal? Okay. So oxygen is associated with combustion or burning of things. Oxygen is what is used in our bodies to create energy. Oh, it's funny. So oxygen is the most abundant element. I'm like, no, it's not. It's 28. In the Earth's crust, or in the human body. You're like, are you serious? Oxygen in the human body? And actually, it goes back to the fact that it's related to the fact that water is so abundant. And of course, oxygen is part of water. I think we're going to skip this one for now. I think we might come back to it. So what else is in the air that we breathe? So, you know, depending on what you wear. Depending on where you live, you're going to have issues with smog. This is Beijing on a good day. This is the same part of Beijing on a bad day. Red days?
Yeah, like in Salt Lake. It's crazy that they get to like listen to the news and they're like, today's a cold red day.
China has to shut down town when they can't even drive.
That's amazing. And seems like I've read that sometimes it's related to the weather patterns,
Yeah,
and
if it's like an inversion, and it'll like
keep it in place. So, and you probably, there are apps out there, and I posted this actually. So like if you live in Beijing or whatever, you can see what the air quality is. Or if you live in San Francisco, you can see what the air quality is. I've downloaded an app, and the air quality is pretty good. So the thing that makes it so dark, of course, some of those are particulates, like little pieces of dust. But like the video we watched said, it's those little particulates, depending upon the size, that it can actually get embedded in our lung tissue and cause significant harm. There are other things that aren't particulates that can give us issues. Nitrogen dioxide, ozone, sulfur dioxide, and carbon monoxide. So, yeah. I want to take a minute, and the ppm stands for parts per million. So here we go. We're talking concentration here, people. So percent means parts per what? 100. So I can't remember what it looks like I kind of hid these. So percent means however many, so like 1% would be 1 part per 100, and it could be grams or liters or whatever. And so we talked about scientific notation in here, right? So 1 over 100 is 1 times 10 to the negative second. All right. So what's parts, how would that look for parts per 1,000? 1 over 1,000. And that's 10 to the negative third. Yep.
Why would that be parts per trillion? Or what would parts per trillion be?
We're coming up, that would be, I don't know if I do that one. Parts per trillion would be, see, billion after trillion. So trillion is this, right? I don't know, parts per trillion. Oh, I see what instead of PPT, what it would be. I don't know. That's a good question. I'll have to check. How about parts per million? 1/1,000,000. And so that's 10 to the what? Negative. Yep, -6, 1,000,000. So in environmental, like data, like trying to say how nasty something is, when they say parts per million, they mean 1 in 1,000,000, usually with regard to mass. But it doesn't take much for some of these things. And then I have parts per billion. So it's 10 to the negative 9. And I don't do trillion, I guess. It's like, so if we had a percent, say we have 0.0402%, parts per 100 would be the 0.0402, right? What would parts per 1,000 be? Sometimes I have to kind of, so compare 100 to 1,000.
Which way would the decimal point go?
So would it go up or down?
Go down, right? So there'll be more parts.
There'd be more parts, so it'd be a bigger number. So it would be.
It would be a smaller number. No, it goes the other way. Because you're adding more parts, so your number's gonna break down more.
Well, let's say we had, you move it left one. Say you have, let's make this 10. Let's make this 10 parts per 100. Okay? What if now we want to know parts per 1,000? Would it be less than 10 or greater than 10? I think it would be greater than 10. Oh, my brain. And actually, that's the way it is. It's so we have more, not less. So in other words, if we're making the denominator, if we're making the thing in the bottom greater, then that increases the thing in the top, because that what we say ratio is going to be the same. We're not quite done, almost. So put another way, I know, we'll even choose this number. 0.0, is it 0.402 per 100 is equal to, what do we do?
0 or 4.
Yeah. By that? No?
Because we increase the bottom, we have to increase the
Yeah, we're scaling up. Yeah, we're scaling up the bottom, and the ratio stays the same, and so we scale up the top.
Okay.
Ah, yay. Okay, so what would the next one be? 402. I'd have to take a minute to, as Jethro would say, cipher it. How about the parts per billion?
I really like that reference that you just had.
The Jethro Bonine, do some ciphering. What would this one be? Yeah, 402,000. Yep. Very good. So that's kind of how they're related. So hold that thought for Monday. You've got to hold it clear till Monday. And I have a question to throw at you related to this. Well, then we'll go back and look at the other questions. So that's it for today.